Hello, my name is William Starks. I'm a researcher for Great Robotics Lab under Dr. Hongbo Zhang. Today I will be talking about how our system diagnoses strawberry plant conditions from a photo. We use a two-stage approach. We have a ResNet classifier that sets the diagnosis once it sees the image, and MiniGPT v2 explains visible evidence along with a next step, recovery step, in order to help remediate the plant. I should cover training, logic flow, and how it works in general. So here is the demo architecture. So we can see that we have the user UI, and it receives an image which is sent and processed to a 448 pixel. This is sent to the ResNet classifier, which is trained on a checkpoint. It looks at, about 2,000 so images, what it's been trained on, to classify out of 7 different diagnostics, and it chooses with what has the highest confidence. And as you can see, high confidence means an accepted label, and that accepted label is injected into the system prompt, and that is a fixed diagnosis. If it is an unknown diagnosis, as in it doesn't have high confidence in anything, then the model is simply told to explain the image the best it can. That diagnosis is rendered and sent back to the user in a form of a caption. Alright, here's the training pipeline architecture. So you start with your data. We used, like I said, about 2,000 plus images, and those images were sent to OpenAI API, and OpenAI API was told to generate image and captions, or question answer pairs, and those question answer pairs are stored in a JSON with human question and assistant answer terms. It is sent to the data loader. We have an auto split for 10% validation to simplify the validation data set creation. That way you can dynamically add more images, and you will always get a 10% validation split. Train.py is going to be your main train program. You configure it with the YAML file. You set it inside. You configure what you need in order to run the program. You set world size, how many GPUs you're using, iterations per epoch, things like that. And you should see, once you're training, you should see a downward loss. You know you're doing good. And you fine tune with LoRa adapters. It's lightweight, it's fast, it keeps the base weight stable. The runner owns the schedule, cosine and warm up, amp, gradient steps. It triggers the validation pass after each epoch and interval. And the decision is made by val loss. If val loss improves, we write our best checkpoint, and if not, we continue training. Image size must match the model's expectation everywhere in the YAML. Make sure that is set, and fix the seed so you don't reshuffle your validation every run. here we have our, hold on, we have our request response sequence, our end-to-end inference sequence, how the user gets a report. So the user uploads an image and sets the temperature. On submit, UI calls on submit, and it saves a temporary image, then calls resnet.classify function. This is where it returns a label, P1, P2 confidence ratings using 2 view TTA and a temperature calibrated softmax. In this demo, top 1 is accepted as the diagnosis. So you can have P2 and P1, and maybe P2 is just a little bit under P1. It's not maybe this, maybe that. It's set P1 will be the diagnostic in the caption. This is proved to so far be good, but I can see where it might not be always the best solution. But thankfully ResNet has been very accurate so far in diagnosing, about 95 plus ish accuracy on average. So the label is sent to the system prompt. The system prompt is built, and we ask the model to explain from visible cues what is wrong, or explain only from visible cues what is wrong, and provide a concrete next step for remediation. Okay, so let's go over some more details within the actual model. Here is train.py, the main program. So first off, alright, let's talk about the YAML configuration. You want to set your model, right? You want to set llama model to where your weights are stored in the file, and your checkpoint to where your extrinsic checkpoint is stored or going to be stored. Here, we set up datasets listed for Strawberry Diagnostic. Images, so what we're training on. Our annotations for these images come from this file path in the form of a JSON, which we used OpenAI API to create using Model 03 for the best visual reasoning. And here is our image path. We set it to 448, size 2, 1500 liters per epoch. Due to the dataset size, data accumulation steps, we did it for 10 epochs on our last fine tune. Let's look next at the demo file. Here's our demo file. We call ResNet immediately. Load ResNet to the set checkpoint. ResNet right here, .pth file. Scroll down, and let me get to it. Here we inject a system prompt. We inject the label from ResNet into a system prompt, and this prompt is used to generate the report in a specified format. We set it to 2000 for much longer reports. It's just worked out a lot better, keeps it from cutting itself off. Let's look at the ResNet classifier. Alright. Let's go to Alright, we open our image, convert it to RGB, So network twice, center and a horizontal flip, average our logits, simple but reliable test time augmentation, Then apply a softmax with temperature, and this calibrates confidence so we don't get spiky probabilities. And I sort and take the top two. There are 7 classes at the moment, but add more, or it gets overridden by checkpoint dynamically. We have thresholds for strict diagnosing, high confidence labels, but at the moment it just chooses what it's most confident in for this demo. But with more training data, implementing these thresholds is not a bad idea. But maybe eventually we could even phase them out with increasing accuracy and less need for thresholds. Alright, so let's move on. And let's get a demo running. Alright. So this is going to be your demo command. So what we do here is set CUDA device to 0, first GPU, set a gradient server name. This is not necessary, but it is safe. We set this to true for GPUs, and we set our config path here. This is the demo YAML, which I should show right here. Here's your demo. I want to make sure it's set to 448. You want your LoRa R and LoRa Alpha set to the same as what you trained. I want to make sure that is set the same. But we launch the demo, and ResNet anchor. This argument, we pass this. This forces a ResNet pass before any language reasoning. The ResNet's top one becomes the fixed diagnosis for the demo. And remember, the language model's job is to justify that diagnostic from the image and make sure that the weights are already in the expected paths. Sure. Alright, so let's do a clean run. And you'll be given a public URL from Gradio. You control click that, open it up, and here we are at the actual system, the actual UI. So here we have enhanced analysis chat box that uses SERP API to use with research, extra context and information. Our standard analysis, which is a quick, basic, visual inspection based off the image and user prompt. So let's go ahead and give it an image. Here is a strawberry suffering from drought, and just let it do its thing. Let's check the terminal. As we can see, our ResNet predictions printed to the terminal with drought at 89%. And we get a confidence badge at the top with diagnostic and cues. The dry cracked soil. Soil is dry and cracked. Lack of moisture. signs. Typical of droughts. Well, there is some greenery or foliage. This is where I guess you could say more training data would be required, particularly maybe healthy plants or better looking plants suffering from drought. But in this case, it does get the correct diagnostic. It does get, you know, a general image. And then it also gives you a remediation step. Address the issue. Immediate action is required. Provide adequate water for the soil. Irrigation system, sprinklers, soak hoses, mulching the soil with organic materials, wood chips or straw helps moisture. Also important to monitor weather patterns and adjust irrigation schedules accordingly to ensure the soil receives adequate water during periods of drought. So not bad. Pretty good remediation step, pretty good advice, and a pretty good in what it's seeing. Let's try something like white mold. Let's check and make sure the label is predicted. White mold, 96% accuracy. Pretty good. Let's see. %, white mold. It shows white fuzzy growth on the surface of the plant. You know, flower leaves and stems. Flower leaves and stems. So we can say that we have a bit of a hallucination issue with this particular example. Growth is dense and covers a significant portion. Well, that is true. Cottony texture appears to be attached. It's true. And see, it's trying to do this A, B, C bullet point format. Isolate the prevent from spreading carefully. Warning can exacerbate mold growth. Treat with a fungicide. By fungicide, according to product instructions. Consider repot. Monitor for pests. Check the plant for signs of pests. Maintain consistent environment. Stress product. Following these recommendations, you can help manage the white mold infestation with healthy growth of your plant. So, pretty decent captions. Like I said, a little bit of issue with saying that there's, leaves and stems. Now, obviously, there's no stems apparent in the image, but it gets the overall diagnosis and picture correct, and it does get about half the visible symptoms on in that caption on a small data set of only 2,100 so images, minus 10% for the validation split. So, not too bad in my. And say we want to train the model. First, we want to make sure that our YAML is configured correctly. Weights are pointed. Storage, annotations is pointed in JSON. Images are correct. Your run settings are set correctly. Want to go. Let's go ahead and clear it. This will be your train command right here. We use both the GPUs on the server. We are currently using two 3090s on this server. Okay. Train.py. Set the config path to train YAML. Press run. see a lot of good things here. Loading checkpoint shards, reads parameters, vision transformer being created. Zero validation splits are resolved. Evaluate. Set to false. Okay, see a start training. And we're currently training epoch 0, 1500 liters per epoch. And you'll know you're doing good when that loss is going down over the epochs. Depending on how much data you're using, you may want to do more than 10 epochs, you may need 20. If it's also a larger data set, you may need 15 iterations per epoch. But I think this is a good general demo of the program and in its current state. I'd say definitely some things to work on right now would be increasing data set size and possibly some user interface improvements. But we've come a long way from where we started, and I think that is all that I have. So, thank you.